give me one more minute.
You were both like her?
Yeah.
That's fine.
She's like kind of to you. I think we get the idea, right? Like we get the idea. We know too. She's not kind of into. So each of the states have to have their own. Let's make state interface. Make state interface. And then it has a state. Unfortunately. Yeah, and the settings. In game, boost game, boost game, pause screen. It's on with this one.
All right, time's up. Sorry, I was really enjoying watching you guys just like okay, let's go through these and chat about them. I really like this exercise. I really enjoy just like watching you guys just like talk about it and just go like, oh, what about this? What about this? And the thing about all this sort of stuff, as you've probably been figuring out over the last like 7 weeks, is that it's not clear cut, right? It's a lot of waffly shades of grey. It's not kind of this is right and this is wrong. And like even there's one example where the exercise was written, and that's like there's one after like this certain one was a composite pattern, and then I think one of you were talking about it, and I went, oh, maybe there's another pattern in there as well. So it's very it's very subjective, and we're going to talk about them now. So sorting collections of records in different orders. Now, when you say what the pattern is, well, I want you to sort of identify the kind of key characteristics that make it that pattern. We kind of talked about that last week with like strategy, state, and observe. We talked about the key ideas for each pattern. So you can say, well, okay, this is a strategy pattern. Well, what are the the things we associate with strategy pattern and how are they present? And try and take it from just from that phrase we've given there. It's not very much, but yeah, you've got like a starting point, and the skill you want to develop is being able to look at a problem or even look at some code and go, there's a design pattern here. I'll talk more about that at the end. But let's go to the first one, sorting collections of records in different orders. Yep.
Saying this is like different orders. That's kind of like saying we have different strategies for ordering these things. So that's strategy pattern is you can choose whatever strategy you want. Get more strategies in the future.
Yeah, for sure. I think you're spot on with that. So let's look at this one, the strategy. And as you say, you've got different orders. Different's a big keyword here. You can chop and change, dynamically adjust your orders at runtime. Yeah, I think it's strategy. Does anyone think anything else? No. Okay. What about the next one? File system. Yeah. Really?
I think like opposite, because when you have files, they have folders above them and folders inside of them, and they can have files above. So you've got like a leaf node structure. You have a composite pattern.
Yeah. There's a sort of tree structure you've got. We're going to do this in a second with the composite pattern calculator, but you've got leaf nodes and compound nodes and a sort of tree-like hierarchy. So I agree with that. Does anyone think anything else? It could do. The thing about the factory pattern, oh, we do that today as well. Sorry, I only thought we had 2 exercises. Is that you can use a factory pattern to create a composite pattern, or use a factory to create. You could have a factory of strategies of decorators. The factory is just the creation. So I think, yeah, what you've got there with the file factory, that's not the composite pattern in and of itself, but you could use a factory pattern to create compound objects. And that's part of lab 7. Yeah. Okay. This one, updating a UI component when the state of a program changes. Yep. Sure.
Because it's got every attribute is coming to your new state. So every program you get seems to be game.
What do you reckon the different states are just from what's given?
Updating UI program. So whenever I think of Windows, I'm thinking like when you click on a file, it can't get highlighted, and that's the state changing.
Yeah, that's interesting. And like I was thinking about this when you guys were doing your state table. And when I taught 1531, we do like remember state diagrams from that, and the sort of I think the way to think about initially it's like I see the state as being user interface state, and like that is a form of state, right? Like the computer, its current state is I've highlighted this thing, I'm on the VS Code README, blah blah blah. But that's not necessarily indicative of the internal state. And you guys understand this in the project, right? You've got your response objects where you can return your world state, blackout, or the dungeon. But then you've also got your internal sort of Java classes and their relationships and their semantics. And that will have some sort of internal state, right? You might update the player's health or something and the state changes. So, when we talk about this one, when the state of a program changes, when the state of a program changes, let's say you have your what we call a model, and then you need some sort of way to say, well, I've changed maybe the player's health, and I want to have that change reflected in the UI, right? Like maybe the health bar, like the health goes down something, and the health bar decreases. And so you have your model on one end, and then you have the view on the other end, and view and UI mean the same thing. And then in the middle is a sort of junction between the two, and guess what it's called? The controller. Now, the view can be lots of different things. We used to run this course, and the front end of the project was in JavaFX. You had to actually build the front end in JavaFX. We took it out because no one uses JavaFX anymore. It's quite old and took up too much of people's time in the project. But what you essentially had was a view written in Java and then a controller. And these two would talk to each other. And then the controller was connected to the model. And we still have the same thing now, but instead of the controller and the view talking to each other as sort of just Java methods calling each other, how does it work now? Response objects, yeah. There's another step, another layer. I don't know if you look closely at the code with you. So the view's the front end, right? It's written in TypeScript, and you run when you like hit run, the front end's already pre-compiled. I won't go into the details, but essentially your front end launches, and your front end makes a series of API calls to your backend, like 1531, right? Your Google Web Server. So the do I have it here? Maybe I have it here. I don't know if I have it here. No, I think I closed all the other ones. Essentially, you have just a server that is a wrapper around the controller, and we've done all the server for you. Just hey guys. And so essentially, you have an API layer, which sort of acts as the controller and talks to the model. Now, okay, what's all this got to do with design patterns? Well, the problem we have is that the controller doesn't matter too much. That's what we would call stateless. It's also kind of hard because sometimes your controller is part of the model, right? You'll have sort of variables and lists and stuff in your controller. So it's kind of this like junction point because it contains an interface, and then it also contains some sort of model specific stuff. But we have the problem of, well, what if we update the player's health, but we need to notify the UI, we need to update the UI. Or what if maybe the user clicks a button to start a battle, some other variation, or they click a button to start a new game. What do we need to do? Yeah, Dave. Yeah. Yep. And what pattern is that? Not necessarily API calls, but just any sort of what are you doing when you click a button? Yeah, you're updating state and you're propagating state And it's an observer pattern because the view goes, well, all right, well, there's been a change in state, right? Someone's clicked a button. Sorry, can I grab my whiteboard? So the view says to the controller, here's my API call. There's been this change in state. We're going to start a new game. And then the controller talks to the model. And this is what you're doing in the project, right? The controller says, we're going to change some methods, we're going to change some variables, however you can manage it. And the key thing is, right, and this is the very fundamental encapsulation idea where the view and the model aren't coupled, right? The front end has no clue how your backend is implemented because everyone implements their backend differently. So this is called model view control. It's essentially just an application of the observer pattern. So the long-winded answer to this question is it's an observer pattern. The reason it's not a state pattern is because you can't look at that and go, here are the 3 states, right? You guys made up some stuff, which is all fine, but the state change causes the notification and the observer pattern propagates the state. You move the state from one place to another. Does that make sense? Cool. Does anyone have any other thoughts on that particular question? Scenario. If not, then we'll do the next one. So parsing and evaluating an arithmetic expression. Any thoughts? I'll give you a hint, we're about to do it. Sorry? Yeah, composite. Really tough one. The parsing though, that was actually the one I thought you could also call this a factory pattern because like you have to do, oh, actually, no, I don't want to give that away. Like you have to do in lab 7, you'll have to pass a composite JSON string into, or composite JSON object into your composite sort of structure. So the parsing could be, you could say it's a factory pattern. All right, this one, adjusting the brightness of a screen based on a light sensor. Observer, yeah? How come? Yep. Any other sort of key characteristics that stand out? Yep.
I'm just a bit confused with the concept. There's only one observer in my mind. It's like, because the light sensor tells the screen, or you could say pixels in screen on the observer. I guess I don't know. That's the only other way I can think of there being any. How is it one to many?
Doesn't need to be one to many. So like you and I could have an observer pattern where like the game we did, you weren't there last week. We did this game for those of you there, and like I'm in the mid, actually no, I won't play it again, but like if let's say we have a different game and if I clap, you have to jump up, right? And so you're going to be constantly waiting and watching me to clap. And so it's a one-to-one relationship, right? But you still an observer pattern because you're observing and waiting and listening, and then there's a state change, right? I clap, and then some sort of event happens. And so there's, again, this sort of propagation of state where it's like, well, I've clapped, and then that gets propagated to you, and then you'll do something. It's all about, like everything, I mean, everything in programming is all about state. The state pattern's more like there are these clearly defined, like you could draw a state diagram just based on what's written there. Like with the YouTube player we did that last week, there are these sort of clear semantic, I mean, like this one's a pretty reasonable example. Like this is a state pattern based on UI. Like if you had a front end, right, you're writing a React front end or something, then I think this would, be a reasonable state pattern to use for your front end. As long as there's sort of kind of behavior that you can abstract and make sense of that sort of thing. Does that sort of make sense?
Yeah.
Whereas this, yeah, whereas state more is more like you have, yes, clearly defined states, whereas this is about the propagation of state rather than the state itself. In this case, it's like the light sensor, and it's like the thermometer example in the lecture where it's like it gets below a certain threshold and then that sends a notification and changes some sort of state. There will be a question in the exam saying, here's a scenario, it'll be more sort of fleshed out than this. And it'll say, you know, what's the right design pattern to use here? And really, like, there could be multiple, it's not, again, not hard and fast, but as long as you come up with a pattern and the key ideas and characteristics and can justify it, then it should be fine. The very last thing, we've kind of spent ages on this exercise, but I think it's pretty crucial. Some of you might know that design patterns get a bad rap in industry and just generally. And the reason for that is, like with your projects, to be honest, I don't love the fact that we're like, you have to use 3 design patterns. That's not something you do in industry, not something you do in real life. The only reason we do that is because we just want you to use the patterns so that you understand the patterns. It's not because you have to use design patterns in your code. It's about, and the thing with the project is like we've specifically designed it so like you should, or you could use this pattern here, you could use this pattern here, and sort of engineered in that way. But in real life, you find that it's not sort of naturally crafted, but because of the way problems in software work, you'll find these patterns will just arise naturally. And you might work on some code and then suddenly realize, oh, this code actually uses a pattern, and no one really talked about it. That was just kind of how they did it. That was just coded up in that way. And you go, oh, that's a composite pattern. Or that's an observer pattern. And like even these are sort of, you know, getting closer to just general real life scenarios. And you'll start to, you know, if you start kind of looking, you sort of see these patterns everywhere. But it's very easy. I was going to bring some cellophane as like an example, but you guys all know what cellophane is, right? Like if you have some blue, I really wish I could get it. And if you've got some blue cellophane and you hold it over your eyes, then everything looks blue, right? With this blue tint on everything. And it's the same idea where like, if you just, it's like, if you go around and be like, where's the design pattern? Where's the design pattern? You kind of go looking for design patterns under a rock. You'll probably go, oh, this is a design pattern. And then you'll try sort of forcing a pattern or the wrong pattern on to something that doesn't really need it, or trying to over-engineer a solution or something like that. So sort of the moral of the story is what we want to do is give you sort of tools in your toolkit. And if the time arises when you're like, we can use a design pattern to make this design better here, or we can use a combination of patterns or something like that, then that's useful, rather than sort of going around and like we kind of do in this question saying, well, what's the design pattern? It's rather like, what's the design? What's the general solution? And maybe we can use a pattern to help us. Does that make sense? Yeah.
Yeah, just like trying to add that. I think a lot of the time in industry you've got like problem that you don't have too much forethought towards it. So that's why like bad design can come about, but then maybe like working more, get like refactored to better design to help.
Yeah, no, exactly. And like you all had this with your assignments and probably with the project now as well, where you're like, you kind of didn't really understand it to begin with. And then once you kind of got into it and started working with it, you coded up some like a solution, and then you kind of realized it was a bit crap. And then you go back and do some refactoring. That's all sort of natural and part of the process. And as you get better, you start to see the patterns earlier and can just do it right the first time. Cool. How are we going for time? 6:41. Yeah, but that's a great point, Sunny.
So just basically like don't force the code to fit it up.
Yeah, the pattern should fit the problem, not the other way around. We'll always give you like any questions in the exam and stuff will be always centered around like we'll have a pattern in mind, and the question we engineered so that you can use the pattern. So it's like that's our side of it. Whereas you'll kind of approach it going, you know, here's all the stuff we've been taught, and I'll just need to sort of mix and match things to yeah. Sorry?
Where you started writing the exam?
Not yet. I've thought about it though. Been busy doing auto marking. But yeah. Any other questions? Cool. All right. Let's do composite now. So if you have an expression, like a mathematical expression, trying to find a good example. I don't think we have any here. So maybe you have the expression 1 plus 2 over 4. Oh, actually, try to make this nice. 2 over 4 times 3, like that. And maybe you're given this. The sort of full problem is you're given this as a string, and you have to evaluate it. We're not going to do the initial bit, which is called the parsing, but we are going to think about how we would represent this and how we could evaluate it nice and smoothly. So the composite pattern is a pattern where you could say, well, I can treat objects in or entity types in this sort of tree abstractly. So if we were to rewrite this as like a tree, say, well, you have a plus, right? And then it's like a binary tree in this case, where each, there's two children here. So we've got 1, and then we have this whole expression as the second child. So okay, we've got a divide expression here, and then there's 2 children of that. One's this one here, and the other one is this thing here. Okay, that's a multiply expression. And then if you break that down, now we just have 2 numbers, 4 and 3. Okay, so there's our tree. That's pretty cool. Okay, now how do we evaluate this? How would you evaluate it if you were just kind of looking at this diagram? Start from the bottom. Yeah. How would you know where the bottom is? Like, what if you have 50 different nodes all along the bottom? So, you get recursion. It's kind of like recursion. We probably used to think about recursion for trees. But let's sort of think about it recursively. You get this node, right? How are you going to evaluate the whole tree given the first node? Yeah. Jim?
The plus will ask. Yes, a plus will ask its children first, like, for what it evaluates to.
Yeah. Yeah, so the plus is just saying, well, I want to add this one and this one. Now we can't just add this, right? So we'll say, okay, we can get the 1, that's fine. And then I have to go and evaluate this as well. So we go to this bit, divide expression. Okay, now what do? We do the same thing. Say, okay, I want to divide this thing and this thing. Okay, we don't know what this is yet. What do we do now? Yeah, so we say, okay, well, now we're going to evaluate both children. So we'll look at this thing, and now that actually works, right? So you can say 4 times 3, so that's 12. We bring this back up here. So now we have 2 over 12, which is, oh, this is disgusting, but like, you get the idea. 2 over 12. And then your final expression is 1 plus 2 over 12 as a decimal. So then now let's code this up. We'll make a new folder called calculator. And the first thing we're going to do is make a, what do we call this? Expression node.java. And this is going to be an interface. Public. And it's going to have 2 methods. Actually, no, it's just going to have 1 method, I lie. So public double evaluate. And now we're going to have 2 types of expression nodes. And in the composite pattern, there are always sort of two broad overarching types of what we call nodes, because this is a structural pattern. This isn't about behavior, this is about representing things in a certain structure. So in this tree example, what are the two different types of nodes we have? Just broadly speaking. Yeah, so we have these kind of leaf nodes, leaves of the tree, which are just values. And then we have compound nodes, which are operations. So let's do the compound one first. We'll say compound node.java, and we'll make this an abstract class, I think. We might change it later. Public abstract class, compound node, and we're going to have a private something. We'll look at this in a second. Left, and private something right. This is an actual code. We're going to fill this in a second. And then we're going to say public compound node. And we'll take in the left and right. Now this is just an abstract class. So all of our plus, minus, divide, times are going to inherit from this. Let's just do the three we've talked about here. So we'll call this add node.java, and public class is going to extend compound node. Now, the other thing this thing needs to do is implement expression node. Okay, let's figure this bit out. What are going to, sorry, let me try again. What are the two types of left and right? Sorry, I'm just missing words sometimes. What are the two types of left and right? Yeah. Expression node. Why?
Because expression node is going to be for like the leaf thing.
Yeah, exactly. The thing with the composite pattern is that you don't care. Like, let's say you're at this level, right? You don't care whether both of the nodes below you are compound. You don't care if they're plus, they're minus, they're A, B, C. They could be literally anything. All that we care about is that they are a type expression node. So you could get a compound node where it's like this. You could get this and maybe a minus operation going on here, or you can get it where it's like the multiply and you just have two numbers that you need to multiply beneath you. So what we'll say expression node. Sorry. And then we'll just pass them both in. I hit down Option on my Mac. It's always different for different text editors and different like if you have a Mac versus Windows. But learn these shortcuts because they're pretty handy. Okay, so the add node, now that's complaining because we need to add a constructor. That's going to be fine. We can leave it like that and then add unimplemented methods. Now, oh, this is annoying. Yeah, okay, we're going to have to make a getter and a setter. Let's do it the easy way. We'll just do getters, but we shouldn't need to reset them later. Okay, so when we evaluate an add node, what are we going to do? When I'm evaluating this add expression, I want to say, okay, well, I've got these two child nodes. What do I want to do with them? Evaluate and add them. So we'll say return get left dot evaluate, and we also need to do something get right dot evaluate. So okay, we evaluate the left subtree and we evaluate the right subtree. Now what do? Add them together, because these are just going to be doubles. This is just going to be a double, one comes back, and then 2 over 12 or whatever that number is will return back up the tree. So what's going to happen here is not recursion, because you're not calling, well, you're calling like a similar function, but it's not the same function. Like it'll be this will be, you know, a pointer to whatever the left node is, and it'll call the evaluate that belongs to that particular node. So you're kind of working your way down the tree. And now basically it's just the same thing for all the other ones. Let's code that up quickly, and then we can talk about it more. So we'll call this multiply node.java, and I'm just going to be lazy and copy it. And what are we going to do here? Times, yep. And let's do divide node. Oops. Cool. Easy. Are we missing anything? Pardon? Oh, sorry. I thought you said, I didn't hear what you said. Yeah, leaf nodes. Okay. Well, how's that going to work? Are we going to extend the compound node again?
So, we're down to using some-
Yeah, we'll call this value node.java. So we'll say public class extends compound node like this. How come? Yeah. Yeah, pretty much. So the reason it's not a compound node is because compound and leaf nodes are two, you know, abstractly different, right? Compound means you have more children beneath you, whereas a leaf means you're, you know, the buck stops with you. There's no more child nodes. So I'm going to say private int value, and then public value node. So this, and I'll draw out the UML in a second, but this is its own implementation of our expression node interface. And just takes in the value. And then what do we do here? And value, yeah. Cool. All right, that makes sense. Let's do a kind of example. Yeah, we'll call this calculator. Yeah, sure. It'll just be up in the repo. Okay, so what we will say is expression node equals new, and we're just going to model this tree that we've done here. So we'll say an add node, and then inside that we're going to say new value node 1. That's the left, and then on the right, new divide node, new value node 2. I'm going to try and make this look a bit nicer. So that's the left. And then on the right is new, what is it, multiply node. And then that is going to have inside it 3 and 4. Cool, and I've got all my parentheses. And now I'm going to say is, oops. Print out node.evaluate. And so that should give me 1 plus 2 over 12, whatever that is. So let's run that. And that looks pretty good. So I just want to go through this again, just in case you still want more kind of clarity. So we go, okay, we make this big composite tree structure, and then we say, okay, let's evaluate the node. So this is going to go to the evaluate method. At the moment, it's just an interface, right? And this is good practice to say, well, I'm not going to say it's an add node. I'm going to say it's an expression node, because all add node expression nodes. And that way you're programming to an interface rather than an implementation. But under the hood at runtime, this will go to the add node evaluate. So we'll say, okay, well, we go to here, we evaluate the left. What's that? Let me just bring this up. So we evaluate the left. Okay, well, that's not good. It's really bad. Okay, never mind. We go to here, we return 1. Okay, that's cool. Let's evaluate the right. Now I've lost all my tabs. We evaluate the right, and then that will take us to the divide node, and so on and so forth. And you keep working your way down the tree. And the key idea is that you don't care what the left and right are. And these could be anything. And you could come along, and we didn't implement subtract, we could come along and add subtract, we could come along and add a trig function, whatever. And your compound node doesn't necessarily, sorry, I told a lie. The compound node at the moment does have to take two expressions. So if you wanted to do something like a trig function where you just take in one value, then you might have to mess around with inheritance, maybe make a trade-off. But at any point in the tree, it's like you don't care who's below you. All you care is if you're a compound node, you have two values, and if we want to evaluate them, if we want to do something with them, then we say, okay, left, go deal with your stuff, get back to me. Right, go deal with your stuff, get back to me, and then combine it in some way. Any questions? Cool. Do you want to take a 1-minute break, and then we'll very quickly do factory, and then we'll go talk about the project. Let's go later. Factory. Does anyone want to briefly go and take a stab in the dark at what is the factory pattern and why might we want to use it? If you've watched the lecture from Monday. No, I haven't watched the lecture. Has anyone watched the lecture from Monday? Okay, let's do this from scratch. So the factory pattern, it's a pattern that is not actually sort of behavioral like observer, state, and strategy. It's not structural like composite. It's what we call creational. And you think, well, what's the use in that? Like, you're just creating objects. You can do that normally, right? You've got the new keyword. That's how we make new objects like we did just here in the calculator. You think, well, this is fine, right? And there's probably two sort of problems. The first is like, how do you make this, right? Like we just coded this up as, we put our example into code, but if you wanted to make a real calculator, we talked about the string passing before, that's its own sort of weird problem to deal with. How do you deal with the characters and the lexicon and all that sort of stuff, which is a nice, interesting thing. We actually give you an example of that in my hand we've done for you. But it's like, how do you go about creating these objects dynamically, right? Because this might change. So that's the first problem. And sometimes the logic for that is quite complicated. So like, especially in this case, you'll want some sort of functionality that its job is just to create the object. And that might be a function, which is what's called the factoring method, which is like just a method in a class. Or you might have an actual, a whole class, which is its entire job is just dedicated to creating other objects. It's just like a factory, it just churns out other objects. So that's the first reason, it's just complexity. And then the second is to do with abstraction. And have any of you heard of the mechanical Turk before? The mechanical Turk? Turk. Not torque, not like turning force. No. Okay, look, mechanical Turk. So there's this, it's like this really old thing. It's basically like a robot that played chess. Yeah, I don't know whether it was actually a robot. I can't remember. I'm pretty sure it was like a robot, but it was basically a yeah, the Turk, also known as the mechanical Turk or the automaton chess player, was a fraudulent chess. I don't know why it was fraudulent, but it basically was, the idea is it's like a robot that played chess. So you could have this like sit down and play I think that's where the chessboard is supposed to go. You could sit down and play a chess game against this robot and it would make moves mechanically. And this is all. Yeah. You've spoiled it. I found there's another really nice picture. Okay. I didn't realize it was fraudulent. I thought that, okay. So anyway, here we go. This is what I was looking for. Yeah, so you have like a chessboard and then there's all the internal workings of that stuff. Now, obviously you think, how do they have that sort of technology back in the 18th century? And the answer is they don't, right? You don't actually have a robot that plays chess. How it actually works is this thing here. They must have moved images because I swear the other one used to be first and they would like scroll down and be like, well, how it actually works is you'd actually just get a dwarf that sits inside the box and pretends to be a robot that plays the chess game. So you think, okay, that's cool. And now here's the problem. The idea is that like the dwarf is hidden inside the box, right? Like the person playing it who doesn't know how the, they don't know how the Turk works under the hood. They have no clue, right? They're just like, wow, I'm playing the robot. But if you do a thing where, well, maybe we've kept that, we've kept the internals all black box and abstract, but then you say, well, okay, well, I want to create a new mechanical Turk, and I'm going to pass in like maybe some cogs, maybe some gears, and I'm going to pass in a dwarf as well. You're like, I wonder how that's implemented under the hood, right? So this is the essentially the idea that when you create an object, you are violating encapsulation almost just semantically, where it's like, well, I wonder what the internals are. You've got a cogs and gear, and most constructors are just like this dot cogs equals cogs, and so on and so forth. So to maintain abstraction, we can have a class that does this under the hood. So maybe we have a Turk factory. Mechanical Turk factory. And you have a method that's like create Turk. I'm not going to do the coding example, but I'm just going to talk about this one. And then you say, okay, well, blah, 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 dot create Turk. And maybe like sometimes you will need to give it parameters. You need to say this, I want this and this and this. But rather than specifying the entire implementation almost like at the outset, where it's like, here's everything the object needs. And as a result, you're sort of violating abstraction by kind of giving a clue to the client how it all works under the hood by telling them what the things you need in it are. You can instead just say, okay, I'm going to create this Turk or this object, and as much of it as possible is done abstractly. And you'll never find what, like, maybe this is a bad example, but it's like in the, I think this one here. Yeah, so we have all these like different entities. And it's like, you need to probably give it an X and Y at some point, unless there's some rules about how you generate the X and Y, which I think there might be in one version of this question. Yeah, it's like, you know, if you want to specify, if you want to specify an X and Y, you'll have to give it an X and Y, but you can abstract and put sort of certain kind of barriers around it if you like. And maybe it's like, oh, it's all done randomly. So you just have a factory that says, okay, I'm going to create a bunch of kings and a bunch of queens and a bunch of dragons at random locations. Does that all make sense? Cool. Very quickly, are there any sort of general design pattern questions about patterns and stuff to do with the project? Not sort of specific, like, you know, what should my code do here, but just like general things. Or anything about testing. Oh yeah, let's talk about that, because then we can look at code and stuff and check in. But just like for you guys writing tests and approaches to testing, that sort of thing, or design. Nope. Okay. Cool. We're making pretty good time. So if there's any other questions on any other content, then let's wrap it up. And stop the